Hi, in this video I'm going to show how to use the SURF and BRISK feature methods from the MATLAB Computer Vision toolbox to detect an object within another image with many objects. In this case, I'm going to detect this object within this image. The SURF and BRISK features are, along with other features, are computer vision techniques to detect interesting characteristics of an image. And what they do is basically for points in an image, they analyze the neighborhood using sometimes gradients or Hessian matrix or other techniques, Laplacians, things like that, and to detect patterns like corners, edges. And if you want to learn more about these features, like SURF and BRISK and others, please see the links in the description, in the reference of the description of this video. What I'm gonna do is detect these BRISK and SURF points within both images, and then finding the matching pairs between the two, and using those points I'm gonna infer the affine transformation to basically translate, rotate, and scale this robot into here in order to be able to mark exactly what it is. Okay, so let's do this example. Okay, the first step is to load the robot image. Let's do that. Here it is. I'm gonna use the imread command and RGB to gray because the SURF methods only want grayscale images, and I'm gonna do the same with the scene image. Then I'm gonna use the detect SURF features, passing only the image, the robot image, and the scene image, and I'm gonna do exactly the same but with the BRISK features. And this is gonna give us a set of points, and the points not only are basically objects of class SURF points, and they contain not only the XY coordinates of the point but also some other information like scale, sign of Laplacian, rotation, metrics, count. And the BRISK point is similar, but it doesn't have the sign of Laplacian, and also they are a class of its own BRISK points. Okay, that is important because when we're going to detect the features, we use the extract features method, and this extract feature method takes the image and the points, and based on the point that's gonna be the features that it detects. So for example, in SURF it's gonna give you SURF features, and for a BRISK point it's gonna give you freak features by default. It's gonna infer it from the points. Okay, so let's take a look at how many points do we have. So we have a bunch of them. We have 9,000 points, but eventually these are gonna be filtered down. Just to give you a spoiler, the number of points at the end is gonna be 10, and around 10, that's the amount of points that we're gonna use to infer the transformation. Okay, so the next, we're gonna just show the strongest 100 points, and this is for the SURF points in the robot image. You can see one in the neck, we have in the Bluetooth and also in the boards. And I think this type of techniques can be very useful in things like board manufacturing, where you have some very predictable environment that things do not rotate much, and in that case this technique can be quite fast and cheap to do the job, like we're gonna do in here. Okay, so let's do the same for the scene. This is gonna be for the BRISK points and also in the robot, and it's almost the same. We have two neck points and maybe something down here that wasn't before. And let's pick up the 300 strongest point, but this time in the scene image. And this select strongest is a method from the computer vision toolbox. Yeah, actually it's related to SURF points. Yeah, the input is basically the points and how many points do you want, and the same thing we're gonna do with these points. Okay, so here again the scene was able to detect more things of the robot and some other objects around. This is interesting. It's like a false positive. there was nothing there. Okay. Okay, now let's extract features again. We're passing surf points for both the robot and the scene, and we pass also the corresponding images. And yeah, the points again are returned, but I understand that none of them was filtered, so we get exactly the same amount of points. And the features, for example, in surf, it's gonna be just an array, and the number, whoops, the number of you can see that we have 9,000 points, so for each point we get 64 values, and those 64 values are the ones that are going to be used to match against the corresponding 64 values of the other points in the another image. That's how you're going to pair them using those features. So let's take a look at one point and all of the 64 features. You can see that we have 64, so that's how they look. Okay, something similar should happen with the brisk points. Okay, so let's match them. Let's match the surf features from the robot and the surf features from the image, from the scene. And we're gonna get a few pairs. And with that, we get only 202. I remember we have 9,000, around 9,000 points, 9,700 points from the robot, and like more than 10,000 for the scene. And at the end, only 202 points match. And these are linear index. This can be confusing again because although the points are x and y, they are stored in a linear index. So the linear index here, we expect the left column is for the robot image, and the right column is for the scene image. And we expect the value of here from 1 to 9,700. It cannot go beyond there. The other one can make it to 10,000 because there were 10,000 points. So now we're gonna use those indexes, use the left column to get the box points, and we use the right column to get the scene points, and we're gonna get all of those points. So you're expecting here the same points that we got originally from the surf, from here, the text surf points. So those are the same points, but they are 200, and the other one is 200 as well because they are pairs. And now we're going to use these show match features that take the two images and take the corresponding points, the pair points, and we're going to display them all together. And we're going to see a bunch of points. There are matching robot points, but also we are matching things that should not match. So we're going to filter a bunch of them. And this function, estimate a geometric transform 2D, is going to infer the affine transform using the pair points from both images, and it's going to filter a bunch of them. So at the end, we're going to get a mask that is going to tell us which of the pair points were actually used. Okay, so let's take a look. Okay, now let's take a look at this. And this is an array of, this is like a mask that will tell us which pair points are valid or not. You can see that most of them are 0 and some of them are 1. The ones that are 1 are the ones that are valid. Okay, so let's see how many of them are valid by zooming them. We only have 6. Well, last time that I run this, I had 10. So there's some randomization going on in here. I'm gonna try it again. Now I got 10 again. Then this is much better. Okay, the good thing is that it's pretty fast. Okay, and yeah, this is using MSAC algorithm. So yeah, that has some randomization on it. Okay, so I'm gonna use the mask to take out the points that are that were really used for this. And now let's take a look again, and we should have 10. 10 surf points for both sides. And now we're going to use the same function with the both images and the pair points, the 10 pair points, to see which one were actually used. Okay, so it kind of focused on the Bluetooth of the robot that actually was in top of the robot, but this should be enough to find a fine transform because they are good matches. Yeah, you can see that the Bluetooth has certain scale and rotation, and this scale and rotation is gonna actually applies for the whole robot, although it's focused on the Bluetooth only. Okay, and now we're gonna figure out the box of the robot here, because we're gonna take the surrounding box and we're gonna transform it to mark the robot in the image with the other objects. So for that we use the size of the image. Let's make the polygon, and that polygon is based on the size of the robot image. You can see that they are using the same maximum coordinates. Okay, so now we pass that polygon points into this function, which is from the image processing toolbox from MATLAB, and we pass the transform. This is the affine transform. You can see in here the top left 4 points are for scale and rotation, and these two are for translation. So we pass the points and we just transform the points. We rotate, scale them, and translate them. And these are the new points, and now we're going to display the scenario image along with those polygons, and to display it we're going to use the line command, and you can see that we use all X points and all Y points, and this should be enough to plot the polygon in the image. Okay, so yeah, the polygon effectively was translated into the correct place, and it was rotated to cover the robot, and it was scaled to have the proper scale. It's not perfect, but it was able to make it. And I tried this with another picture of the robot, in which the robot had a significant, a very different three-dimensional angle from the one that appears in here, and it did not work. It looks like these feature detections are good for two-dimensional translation, rotation, and scaling, but they are not very good in three-dimensional very big rotations in the 3D space. And maybe for that maybe deep learning techniques might be better. But if there's not much rotation, the rotation remains in the two-dimensional space, and the objects are quite predictable, then these feature detection techniques could be useful. They are fast and they're easy. They don't require training. They don't require a bunch of data. So for certain cases, it could be convenient. Okay, that's all for the video. Thank you very much for watching.